Hello and welcome to my presentation on supply chain attacks and install scripts at AppSec Village at DEFCON 29. Before I start, I would like to thank all of the organizers and attendees for making this talk happen. Here's basic outline of my talk, a little bit of an introduction. We're going to talk about different supply chain attacks. I'm going to talk specifically about the curl bash pattern, talk about how we do verification of scripts that use that pattern, some tooling that I developed, some interesting things that I found along the way, and we'll finish up with takeaways and hopefully a questions and answer session. So as an introduction, what prompted this journey? So in April, it was discovered that a bash script used by codecov.io, which is a code coverage tool, has been compromised for at least 3 months. Here's a screenshot from the codecov.io compromise page. There's a lot more information available there. But essentially, somebody gained access to the script, and since early January, it has been compromised. They injected code, and as a result, codecov.io users, thousands of organizations, tens of thousands of users, and they're running malicious code within the environment. When I saw this originally, kind of it looked interesting to me. And one of the things that looked interesting is this something that's limited to this particular vendor, or is this something that we use every day? And I went out and started looking at other places where this pattern is used. Now that we know that this thing is possible, that a compromise of this nature can happen, how do we go about making sure that it doesn't happen again? So I'm going to be talking about supply chain attacks, but specifically I want to focus on what I think is a corner of the supply chain which has not been looked at before, which essentially is these shell scripts that use what I call the curl bash pattern, and talk about some verification methods, some approaches, also some tooling, interesting findings. Before I start, just a little bit of an introduction. I'm a software developer, have been a software developer most of my life. Did security always on the side. For the last couple of years, I've been privileged to work in security full time, but I want to be very clear. I am not here representing my employer. I'm here in personal capacity. I present before a bunch of other conferences. There's a bunch of anti-spam things out there that I've been involved with, some RFCs. Security.txt is something that I've been recently working on, helping out at Overflow, who is the original author. It's about to become an RFC, and there's also some other RFCs that I have done in the past. Here are some CVs that I've discovered. Also want to be very clear is two things. One is I'm not blaming anyone. There's going to be a lot of vendors and open source projects mentioned in this talk, but it's not their fault. Security is something that we all have to do, and it's not an easy thing to implement. Many open source projects are often working for free. The second thing is also my standard disclaimer, as you can see the screenshot below from War Games, don't do anything without talking to a lawyer. There's some techniques here and that I'm going to be presenting that may lead you on a chase to do something you're not supposed to be doing. So once again, don't do something without talking to someone in the legal profession. Before we start talking about the particular pattern of curl bash and install scripts, let's talk about software supply chain attacks in general. Modern supply chain, due to its nature, includes a lot of different phases. There's the design of the software, there's the development of the software. While the software is built, it gets distributed, and then you have to get it from wherever it originates from to the organization that's using it. And even after that, there's updates. Because a lot of things are no longer done in-house, and there's a lot of shared code out there, modern software includes third-party components that come from both open source and commercial sources. In addition, even without that, developer tools, infrastructure, CI/CD tooling, a lot of things that are around the business of building software also use a lot of third-party components. Even after software is built and is ready to go out the door, software distribution and updates, a lot of the infrastructure there also uses third-party components. There's CDNs, there's web servers, there's buckets. Developers and security teams often don't know what's inside these components, how they're delivered, and how they're legit, whether the source it originates from matches what you actually have in your hand. And anywhere along the line, any of these pieces can be compromised. This is what many people imagine the software supply chain to be. You have a beautiful castle. In reality, it's more like this cartoon. Underneath a beautiful piece of software, there could be an open source component that somebody has been maintaining on their own for many years for free. And what if that component is compromised? And what if the maintainer of that component has been changed and now works for a nation state? So the reality today is that even though it may look like a beautiful castle, underneath there's a lot of pieces that may not be so beautiful. Now, what are software supply chain attacks? A software supply chain attack targets any third-party components infrastructure that uses software development delivery. Sometimes it's third-party, sometimes it could be something that a company owns but located somewhere else. Usually, what an attacker tries to do is to replace a legitimate component or inject malicious code. Sometimes that may take a form of actual code. Sometimes they may target infrastructure instead of the software itself. What is the goal of these attacks? The goal is that they are trying to get a foothold inside organizations that are using the software that's being built. And then usually that gets followed up by something much more nasty. Once they get the initial foothold through the door, through the compromised software or infrastructure, there's usually things like ransomware, stealing data, or something of that nature that comes along the way. In the recent years, a lot of these attacks, due to the sophistication required to pull them off, have been done by APTs and nation states. Now, some examples. This is just a picture from the Atlantic Council report in 2020. They tried to go out and catalog how often did this happen. There are 115 attacks that they have in the catalog. You could follow the link to the paper. Various different stages, as you can see here. 32 are in the beginning where the software components originated. Some of them, 6 compromises the case. You got open source repositories that were compromised. You got some sort of account access attack where I'm assuming probably developer account that gets compromised. You got App Store compromise. You got updates. That's the flavor of the month. Updates are often also compromised, and things of similar nature. Here are some examples that have happened recently. Not all of them necessarily malicious. CDNGS, Cloudflare CDN that serves open source components. Research has shown that it can be compromised. The bug was fixed. Some research from Alex Burson recently also showed how you can compromise modules that come in from public repositories. CodeCov, as I mentioned, happened also. SolarWinds, obviously, is the big one. That happened December of 2020. There's have been multiple attacks involving Xcode projects because Xcode can execute binary code. Developer downloads some Xcode project they saw on GitHub, they get compromised. Famous Twilio SDK compromise because of a S3 bucket that was misconfigured. NotPetya, malicious piece of software allegedly from the Ukrainian government, released a virus. Also, too many to count, malicious modules in open source repositories. This happens all the time. NPM, GEMS, Python repository, Java, to a lesser degree, happens all the time. Mage card attacks. The mage card attacks is when JavaScript gets compromised in a web page. Sometimes those compromises happen from a piece of JavaScript that comes from a third-party vendor. And obviously many, many more. What can we do? So before we can even talk about solutions to supply chain attacks, one of the things that's very important is awareness. Do you know what's inside your software? What's in your infrastructure? What's inside your tooling, your CI/CD system, your artifact repository, CDNs? Do you have awareness of all the different pieces that are used to build your software, or all of the different infrastructure that supports it? And once you know what it is, do you even know where it comes from? If you have a release process, which I hope you do, who is in charge of it? What's involved in getting raw source code into an actual release? These are not easy problems to solve. Very often, you could go down a rabbit hole. You could have a component that uses a component that uses a component. Same thing for infrastructure. Today's infrastructure is no longer just a simple web server. Many times, there are third-party pieces. There are CDNs, there are package stores, there's all kinds of cloud stuff. And then if you're an organization that publishes and updates software, do you know what's involved in your update process? Are those updates digitally signed? The reason why this talk is called the Poison Diary is because for those of you who are Harry Potter fans, this is a poison. There is a magical artifact called the Diary that was running essentially magical code, turned out to be malicious. And the point of the diary was you should not trust anything that can think for itself if you can't see where it keeps its brain. If you are not controlling the particular component that you're using in your software infrastructure, or if you're not controlling the particular infrastructure itself or the CI/CD process, how do you know what's going in there? How do we secure the supply chain? This is a very, very hard problem. The basics which are the requirements, are pretty simple. If you're a consumer of components, you just need to make sure the component you are getting matches what the original project or commercial vendor actually produced. In addition, you also have to make sure that whatever they're giving you has not been injected with malicious code. If you're a vendor or if you're an open source project maintainer, one of the goals that you have is to making sure that whenever you publish something, it actually matches the original source. At the same time, you want to make sure that nothing was injected into the original source. But these are not easy problems to solve. Here are some approaches that are found in the wild. So some people choose to outsource security to third parties. For example, in my research, which I will show later, there are people who rely on direct GitHub downloads, meaning the script that they're using is located in GitHub source code that bypasses the entire infrastructure used for builds. And you're getting the script essentially directly from the source. Some people choose to rely on package managers because package managers have a more narrow release process. People who are putting stuff into package managers are supposed to have some semblance of control over their software. There's also a push to do some cryptography. Checksums, which we'll talk about later. There's OS digital signatures. So for example, Gatekeeper in macOS, there's Authenticode in Windows, using certificates to sign things. In a Linux ecosystem, you could use PGP signatures. PGP signatures straight up, we'll talk about that as well. Public key ecosystem, there are ways to get a code signing certificate from a public certificate authority, just like we do with SSL. And by you trusting that ecosystem, you end up trusting the certificate. There are attacks in that as well. There are some other ones. You could do an antivirus scan. Unfortunately, that doesn't necessarily find something that's new. You could disable automatic updates. Then you get to lose if there is some sort of a flaw in the software you have. There's going to be a delay till you've applied the update. There's perimeter defenses. You could have, for example, your CI/CD system locked up. You cannot go call out to the internet, but it makes things harder. You could do detonation, where you could try to download the update and see if it does something malicious, kind of behavioral pieces. There's manual review, which is sometimes easy, sometimes hard, but requires humans. There's some experimental approaches that haven't taken off yet. For example, reproducible builds. There is a push out there to be able to take a piece of software and build it and seeing if that piece of software matches the official release. Because of the differences in how builds are done, it's not an easy thing to pull off. And obviously, there's blockchain. So now that we talked about supply chain attacks in general, let's talk about the particular corner of the supply chain that I have been looking at for the last couple of months. This is what I call the curl bash pattern. What is the curl bash pattern? Here's an example from Homebrew. If you want to use Homebrew, you essentially use curl to pull the installation script and you pipe it into bash. This pattern uses curl bash or wget bash or some similar approach to download a script from the internet and execute it automatically in your shell without anything in between. It's a very convenient way to install software, especially if you want to do something like bootstrapping. There is a long-standing debate. Is this safe or not? My honest opinion, it is not safe because you are executing code that originates from an outside system without looking at it first. Historically, security concerns with this approach have been downplayed, and here are some of the excuses that people have used. Oh, don't worry about it. A user will review the script before running them. Or these scripts are not used often. Like how often does somebody install Homebrew? Third one, a malicious actor can compromise other things just as easy. And I will talk about some of these. Now, reviewing scripts. An average shell script contains Unix commands. Here's an example from xkcd, which I'm sure many of you can relate to. Unix commands use very complex command line options. So here's an example using tar. Can you solve this problem? Can you type in a tar command without Googling? I cannot, and I bet you many of you cannot also. The same thing applies to the shell scripts. Many times a shell script is pretty obtuse. So if we cannot rely on users to be able to read a shell script, Here's another example. CodeCov that I mentioned earlier. The script was used by thousands of organizations, tens of thousands of people. The way the issue was found is through checksums. It was not found by somebody who was reading a script. So if you have 3 months of usage, you have tens of thousands of humans, machine CI/CD pipelines, etc. Not a single person realized that they were using malicious code. The only way we found the problem is because the attacker forgot to update the checksum file. Another example, here's pip. This is one of the ways to install pip. It's not the only one. The way I found this is because I was monitoring for changes in the pip script over time, and I couldn't view the changes. It turns out, and they tell you that straight up, pip includes binary data in the end. It's base 85 encoded Python. So if you expect your users to actually read this, it's not readable. I actually went through the trouble of running a small little utility, trying to see what it would take to actually decrypt this, de-encode it, look at it. It produced a whole bunch of different files, which were not easy to review. Another example, going back to CodeCov, since the incident has happened, CodeCov has come up with a new idea. Instead of using a shell script, we will now use a binary. So before, if you were expecting people to review a shell script, now we have to blindly trust someone with a binary. And once again, like I said earlier, I'm not blaming CodeCov. This is a common issue with many, many different projects where we have to go and blindly trust a binary. Here's another example. One of the concerns that people mentioned is that, hey, it's not a problem because it's not used very often. It's usually used by humans. It's usually not something that gets run on a frequent enough basis. Here's an example. If you could look here at line 213 and line 214, this installs Rust from a shell script. This is part of a Docker file. That is part of a project, part of an open source project called Dependabot. Again, not blaming Dependabot, but my point is that historically, these scripts do not always end up being used by humans. They end up being incorporated into CI/CD systems. And it's not just about scripts. If you look further down, line 221 and 222, you could see a similar approach where we're downloading some other thing from HashiCorp. It's not a shell script, but the concept is the same. There's automation happening here. And if somebody were to interfere with these files, a lot of projects that are relying on this automation will become compromised. Like I said earlier, we don't want to trust something unless we know where it's coming from. And this is very true for these shell scripts because a lot of times these shell scripts are not something that you have an opportunity to review. You don't look at them. So why are we trusting them? How common is this? One of the other concerns that was raised, and when I had discussions, is this really something that's common? So I went out and I started collating a list. This is one of my projects, which I will show you later. I want to show, I want to see how common is this thing. So unfortunately, this is fairly common. The good thing is that this a lot of times is not the only way to install something. A lot of times is an alternate way which is more secure. The downside is if you want to verify whether these scripts are actually legit, it is not an easy problem to solve. But the bottom line is, do you even know if this pattern is used in your organization? Here are some examples. Here are some projects that use this pattern. So you got, and I'm going to show you some examples later on. Azure. You want to do the Azure CLI. Now, to their defense, it's not the only way to install Azure, but if you want to install it from a script, this is how you do it. Dell firmware update. You want to update this particular server. The way it's done is using this particular script. Firebase, there's a CLI tool for Google's Firebase. You want to install the tool, this is how you do it. Again, coming from a shell script. Obviously, Homebrew that I mentioned earlier. Pip is another example that I mentioned earlier as well. Rust. Rust is also, it's a fairly new programming language becoming very popular. The way to install it is using one of these scripts. Now, if you are doing install scripts, and this is how you bootstrap, if I'm an attacker, what can I do? So scripts, just like every other piece of software, comes from the original source code to a distribution point. In CodeCov's example, it ends up on some web server. Unless you're doing direct downloads from a source code repository, like for example, in the Homebrew case, it's coming directly from GitHub. It's going to go through some third-party distribution point. You could target anywhere, any infrastructure along the way. Web servers or CDNs. So CDN-JS, third-party CDN hosting JavaScript. It copies the JavaScript from some source, puts it on CDN, by Cloudflare. Recent research has shown it can be compromised. Cloud buckets. You stick something in the cloud bucket, you forget to configure it properly, can be compromised. Twilio SDK got compromised that way. CodeCov, one of the underlying issues was some sort of a Google Cloud issue with the bucket. Build systems. SolarWinds, if you look at the report, SolarWinds was compromised by something being injected into their build environment. Original source code repository. PHP recently had an attack directly on their Git server. You don't necessarily have to go after those systems directly. You could go after the people who have access to those systems. In my opinion, these are novel attacks. Why? Because these things are not common. Shell scripts are not as common as, for example, an npm module. But you get a bigger bang for your buck if you're an attacker. Just think about it. What would happen if Rust installer or Homebrew are compromised, even for a couple hours? Now that we know that these scripts exist, and they represent some sort of a security risk, one of the other things that I wanted to research is if I want to do the right thing and to verify that these scripts are legit, how do I do that? Let's say you want to do verification. So I looked into how that can be done. This is not an easy issue, especially with cryptography. PGP becomes very complex. I did some tooling. I also been running it for several months. I reached out to multiple projects and commercial vendors. Most unfortunately refused to implement the request because they do not consider the risk to be significant enough. Like I said earlier, I do not blame them. We are only aware of a handful of attacks on these particular scripts. There's other issues that also came up. But at the end of the day, if you want to be secure, what do? Easiest thing, don't use them. Don't use the script. In many cases, there's another way to install something. Instead of using a script, you could use a OS package, you could use a language package. Some offer official releases in binaries. Those are not perfect. They can be compromised, but they're not is necessarily compromised in the same way. And a lot of times they're harder to compromise. There's also a formal release management. Scripts often don't have formal release management. They're not versioned and they're not released. Formal release management helps because you have a narrow pool of people who could do that as opposed to everybody who has access to the infrastructure. This is not, again, something that could be convenient in a lot of cases. Shell scripts are very convenient. Another option, you could go directly to the source code. Like the Homebrew case I showed earlier, you could check the script directly from the source, bypassing all of the third-party infrastructure. This relies on Linus's law. Enough people see it, someone will notice something. The flip side is that when you have a source code repository with many committers, only one committer needs to be compromised. If it happens, let's say at night when the other committers aren't there, it could be, fairly dangerous. Changes to source code all take effect immediately. Unlike when you have releases, which takes time, um, this can happen as soon as the attack happens. You can review the source manually. You can save a good version, but a lot of these scripts are not versioned, and therefore, essentially what you're pulling is the latest and greatest. And one example that I found, again, this is an example of Homebrew. Again, not blaming them. This was a mistake. Back in 2012, one of the developers made a mistake, and for about 10 minutes, the Homebrew script pointed to a different repository. So as the result, for 10 minutes, somebody was downloading something else that was supposed to. The developer originally found and reverted. Next, another method, checksums. Many projects publish checksums. So for example, here's the case with CodeCov, they were publishing a checksum file. If you think about it, checksums are useless for security because an attacker can modify them. But as the CodeCov case has shown, it is an extra barrier because the attacker has to be aware of it and go ahead and change the file. You could also choose to host the checksums in a separate server. You could put them into the code repository. Now the attacker has to compromise two servers. The same thing goes if you want to compare the script. Let's say you have a CDN, you want to compare against the original. There's another option. There's also an option of doing this in the browser. SRI, if you do checksum in a browser where the CDN suddenly changes, that really works well, but it only works because you in the browser, JavaScript components are usually versioned. You could go a step further. We can do cryptography. So some OSs can let you sign things with a CA issued certificate. Chocolate uses this approach. That uses the CA infrastructure in the case of Windows. In the case of Mac, it uses Apple's infrastructure. There are issues with certificates. You could get a stolen certificate, you could get a legit certificate, but it's still better than nothing, and it's not bad. You could also do PGP. You could use PGP, you could create a separate signature, but it's not CA based. So in a CA case, you're relying on the fact that CAs have some sort of checks. In PGP's case, the problem you run into is key distribution. If you want to verify that a project is legit, how do you distribute the key? If you put it on the same server, the attacker can change it. If you have a PGP key server, those could be poisoned. I have not seen yet attacks that involve compromised keys, but it doesn't mean they cannot happen. Here's an example of Chocolatey. As you could see, the Chocolatey script itself in the end has a cryptographic signature. Here's an example of NixOS. They're using PGP. And when you are installing the original install script, which is on top, you can go ahead and pull the specific keys and signatures. They're using, as you can see, a key that's identified by an ID, by fingerprint from a key server, and you can actually verify that the script is legit. In summary, best thing is to avoid shell scripts and use package managers, but not necessarily be as the safest option. It's going to depend on the particular use case. You could do checksums, you could download from source, you could do comparison against another version. It helps as long as the attacker forgets to update both files or if it's hosted on both servers. The cryptography works better than most of these approaches. It is hard to set up and use and it has its own issues. Like I said, key distribution attacks with PGP. CA certificates have issues as you could get an illegitimate certificate or you could steal a certificate. Most projects that I looked at do not provide any kind of signatures. Bottom line is organizations need to make their own decision. If you're using these scripts and you want to verify them, it is up to you to make a decision how to do it properly. And we still need more work and more research on this particular area. Let's talk about tooling. And I also want to share some things that I found. So tooling. One of the things that I wanted to find out if I want to do verification of these scripts in an automated fashion, how do I do that? I also want to see how often these updates happen. Is there a lag between, let's say, a signature being updated and the actual file? I want to monitor scripts for changes. I was curious about what kind of changes happen in install scripts. The existing tooling wasn't really there. I happened to write some of my own, but it is kind of experimental. The best way to do verification, let's say using PGP, is to use a tool like GPG directly. Those tools are not always easy to use. One of the things that I ran into is it changes machine state. When you download keys, it changes the key ring on the machine you're using. I didn't want that. I want something more clean. There are ways to do that by using temporary directory, but again, I wanted something a little more cleaner. I also want to have some configuration. So I created a bunch of experimental tools. The first one is just a GitHub project listing various different projects using this particular pattern. There's some blog posts, this talk, obviously. Also, like a suite, what I call Ice Trust. It's a tool that lets you actually verify downloads, some dashboarding around it, and also there was another tool, Release Auditor. I found a bug in GitHub, which I'll talk about in a little bit, but it's not really connected to the rest of the tooling. What is iTrust? iTrust is a Python module that lets you verify files you already downloaded. So basically, you're doing your curl, you get, double you get, and then you are using this tool by either comparing two different sources of script, or you're doing a checksum file or PGP. This is what I call canary mode, where you can have JSON configuration files that can be run on a regular basis. Very useful for an open source project or a vendor that's publishing stuff and wants to make sure that make sure that the stuff doesn't change. Some dashboarding example, like nice visuals to see if you could see like multiple projects at the same time. There's some Twitter account that also gets results. Under the hood, it uses GitHub Actions. You could take a look at the code. GitHub itself is used to store changes. Here's just an example. I showed it earlier. This is just a simple list of projects, name the project, what the script is, if there's any particular litigation, link to the original issue, if it's known. iTrust. iTrust lets you essentially do things that you could do in GPG, but a little bit easier. If you could do GPG, you should do it yourself. So example here, you do your curls, You download the files, you download the signature, and then you essentially run my tool against it with the key that's known. If you want to use the key file itself, you have to download it separately, and you could do it that way. Again, you could do this with GPG, but I decided to do it this way because I wanted to script it in order to do this on a larger scale. Here's Canary mode. Canary mode is where you have a JSON file. A JSON file essentially includes information about the project. And instead of doing the curls the curls yourself, the tool will do it for you, and it can also output some data. Dashboarding. This is a very simple GitHub Actions, GitHub Pages Jackal configuration. Takes the JSON file, and what essentially this does is it looks at verification results on a regular basis. You can also follow the links, take a look at the file being changing. Here's an example of a file being changed. Here's code.conf. You could see that, for example, 2 days ago, the version was changed using regular standard GitHub blame. And something a little more fancy is iTrust Uptime. It uses called an open source project called Uptime. It lets you essentially look at it kind of like a status page type thing. It also, as you can see here, it also lets you, it opens GitHub issues automatically to kind of track historically what was changed, what was, verification failing. Twitter account just tells you, file content changed, verification failed, verification passed. How do they, now, what do I do with these tools? So I document 25 projects that use this pattern. There's a whole bunch more that I reached out. Still going through the query disclosure, can't talk about them yet. Monitoring signatures on 5 projects. Like I said, most projects don't offer cryptography. Also looking at where there's 2 different copies, looking one against the other. Monitoring some for changes, runs every 6 hours, piping it to all of these different places. Eventually looking at incorporating into my own projects, but right now it's more of an experiment. I have been running this since April. What did I find? Only a minority of projects offer a way to do cryptography through PGP. Most projects and vendors are not interested in the fix. They don't consider this issue to be important enough, although I suspect if these attacks become more common, that may change. There's usually better alternatives in most projects, but not all of them. Raw GitHub downloads is a fairly common pattern. That's how a lot of projects kind of bypass those infrastructure challenges. Most of these scripts don't really change very often or change in very minor ways. Some cases verification is not trivial. You have to parse them to get a version number. From the version number, you have to go to a branch. There is a lag that happens sometimes from the time a script is available until the signature gets calculated. I suspect some projects haven't gotten their release management done correctly yet. The downside is that happens and you're doing verification automatically, the automation fails. There's often no formal release management version for most scripts. The good thing is no supply chain attacks. I haven't found a single active attack as the result. And it is possible to do monitoring on a larger scale. Some incidental findings. Bug in GitHub, you could go and modify a release without anyone else knowing about it. I let GitHub know. They don't consider it to be a bug. I wrote this tool called Release Auditor. You could take a look at it. Another surprise was Firebase CLI from Google. For whatever reason, it's calling Google Analytics. Could be a privacy issue for those people who are concerned. Some scripts don't match the source code. When I want to do comparisons, there are some slight differences in the source code. It's a bit of a problem because it's kind of hard to tell why they differ. The research is still ongoing. Now, what can we take away from this entire journey? We need to have more awareness about what's in our software, tooling and builds. Remember, like I mentioned earlier, the poison diary. You need to know where the tools we're using they keep their brains essentially. The use of bootstrap scripts, in my opinion, is dangerous. There are safer alternatives, but you have to evaluate your own risk accordingly. Not everyone agrees the same way, and I, can't say across the board this is dangerous in every single case. It is possible to verify some scripts, however, it's not a trivial case. You must be prepared for things that can break. If you are publishing scripts or software yourself, consider monitoring them, for changes. That could be an additional control. Formal release management is important. These scripts don't necessarily have formal release management in most cases. Less people have access. There's less things to compromise. If you have formal approval, if you have 2 people approving it, there's a lag between when the source code is modified till it's published. Use native tooling. My tooling is experimental. You feel free to play with it, but it is experimental. And the last thing is, don't forget the rest of the software supply chain. These scripts, it was a fun project for me, but it's just one tiny corner of the overall software supply chain challenge.